Hello, chemists! This is Ms. Placino, and you're watching Lesson 12.1, An Introduction to Acids and Bases. In today's lesson, we're going to talk about differentiating between acids and bases. Goals for today's lesson. You should be able to recall the general properties of acids and bases. We're going to associate different ions with acids and with bases, specifically H plus and H3O plus, hydrogen and hydronium ions with acids, and then hydroxide ions, OH minus, with bases. We're going to be coming back to that concept a lot this unit, so we're going to kind of set up the foundation today. But the big goal for today's lesson has to do with naming. Acids and bases, actually mostly just acids, have a very specific naming rule that we're going to have to follow. So you should be able to name the acids when giving the formula, and you should be able to provide the formula when given the name. All right, let's get started. My guess is you might have a little bit of knowledge about acids and bases from previous classes. Hopefully one thing you remember is that acids and bases are always aqueous solutions. We're always going to be taking some compound or molecule and dissolving it in water. If we take a look at HCl, some students see this, especially if the symbol gas isn't there, and they call it hydrochloric acid because they've seen it in previous classes. As a gas, we call this binary molecule hydrogen chloride. If you want hydrogen chloride to behave as an acid, we've got to take the HCl and we've got to dissolve it in water. Once you dissolve hydrogen chloride in water, it's going to dissociate into ions. Specifically, as you might guess, the H plus and Cl minus ions. It's that presence of H plus ions that is going to make something acidic. You might be looking at this thinking, well, wait a second, isn't that a covalently bonded molecule? We know covalent bonds don't dissolve simply by adding them to water to form an aqueous solution. When it comes to acids, usually we're going to think of this bond as being a little bit more covalent in nature, ionic in nature rather than covalent in nature. And we will see the hydrogen and chlorines kind of splitting from one another to form these two ions. Let's look at some general properties of acids and bases. So we're going to play a little bit of chemistry Pictionary here. We've got a couple different pictures. I want you to see if you can figure out what we're trying to convey with each of these. So that picture up at the top, hopefully you recognize that apparatus from previous demonstrations. It's our conductivity meter where we test to see if a solution can conduct electricity. The light bulb is glowing, meaning this solution conducts. So what are we trying to convey here? Yeah, acids and bases are going to form electrolytic solutions. Remember, electrolytic just means can carry an electric charge. What about that mouth? What is that probably trying to tell you? Yeah, something you should not do in the lab, the way chemicals are going to taste. Bases taste bitter. You can match up the B with the B, and acids taste sour. If you're somebody who likes sour candy, like Sour Patch Kids or Sour Warheads, if you check the ingredient label, I bet you see a couple of acids, including something like citric acid, which is going to give it that sour taste, but be safe for human consumption. Third picture, somebody's washing their hands. This has to do with how one of the substances feels. Bases tend to feel kind of soapy or slippery, so if you have it on your hands, you are usually pretty aware of it. It feels slick. Acids just feel like water, so it can be a little bit more difficult to detect when they're on your skin. If you were to measure the pH of most of the soaps that are used, actually all of the normal soaps that are used, you should see that they've got a basic pH. I don't have a picture for the next one. Acids are corrosive to metal. You can kind of think about that as acids are going to be reactive with metal. Like if I take a piece of zinc and I put it in hydrochloric acid, that is definitely going to react. The zinc is going to turn into zinc chloride and hydrogen gas would be produced. What about these little strips of paper? You might have used those in a previous science class. Yeah, these are litmus paper, and litmus is an indicator that's going to help us gauge the rough pH of a substance, namely, is it acidic or basic? Bases are going to turn red litmus blue. Again, you can kind of match up the B and the B, and acids will turn blue litmus red. Be careful here. Students often kind of confuse like what color the litmus paper should be to start. Well, if you try to test for a base with blue litmus paper, it's not going to turn any bluer. So you want the opposite color to start. And there's really no way you can guess what this last picture is about. But it has to do with the chemical reaction that's going to occur between Arrhenius acids and bases. An acid plus a base is going to yield salt. When we say salt, we mean just any ionic compound. It depends on which acid and base are being used to neutralize one another. That does not necessarily mean sodium chloride. And will produce water. But a lot more information about neutralization reactions will be discussed in upcoming lessons. All right, so that's just kind of an overview of some general properties of both acids and bases. We're going to define anything as an acid that releases hydrogen ions into solution. So if I take my compound or my molecule and I dissolve it in water and H+ ions are produced, that substance will be considered an acid. So acidic solutions are going to have high concentrations of H+ ions. Well, if water floating around in solution, you'll have some degree of hydroxide ions, but you can see these like little red hydrogen ions are the dominant ion in solution. Bases are going to be any substance that release hydroxide, OH- ions, into solution. So as you might imagine, we should see kind of like the opposite picture of what we've got on the screen right now. Lots of those yellow OH ions floating around and comparatively few H+ ions. So we'll see very low concentrations of hydrogen ions for bases and lots of hydroxides. And that's really what makes a substance acidic or basic. Acids release hydrogen ions into solution, bases release hydroxide ions into solution. So the big focus for today's lesson has to do with naming. I'm going to start with naming bases since this is something that we've actually done before. Most of the bases that we're going to look at are going to contain a hydroxide group, also known as just a hydroxide ion. These bases are named the same exact way an ionic compound would be named. So we've named plenty of compounds that have hydroxide present. For example, if we looked at NaOH, just like we'd name any other ionic compound, the metal will keep its name. We're talking about a polyatomic ion, so there isn't any change that should be made to hydroxide. I would simply call this sodium hydroxide. Sodium hydroxide dissolves in water to produce hydroxides. It is a base. Ooh, let's make it tricky. Let's give you 2 hydroxides. It's the same naming convention. Metal keeps its name. We don't use prefixes because these are ionically bonded compounds. We would, of course, just call this calcium hydroxide. So nothing really new to focus on when it comes to naming bases. That is not the case when we talk about naming acids. Most of the acids that we look at will be Arrhenius acids, meaning there will be a hydrogen ion present or a hydrogen atom present if it's a more covalently bonded molecule. So all acids have hydrogen, so it's really going to be the anion that's present that is going to impact how we name. You have to be really careful about which anion is present. So we're going to look at 3 different examples before we get into some practice problems. We'll start with a monatomic ion, something like the chloride ion. These 2 remaining are what we call oxyanions, oxyanions, as an oxygen, or in this case 3 and 2 oxygen atoms are present. We have chlorate, ClO3 with a charge of -1, and we have chlorite, ClO2, also with a charge of -1. Let's put those up there. And the key to naming our acids is really looking at the ending of each of our ions, whether it's an ide, an ate, or an ite. All right, let's start by naming binary acids. We know the prefix bi means 2, so we're talking about acids that tend to just consist of 2 atoms. Let's look at HCl. We know that HCl as an acid is named hydrochloric acid. Let's try to break down what we did to name this. We know that usually this is hydrogen chloride before it's dissolved in water and becomes an acid. So it looks like my ending, my "ide" became an "ic." When you take a binary acid, you want to drop the IDE ending of the anion. So things like fluoride, chloride, bromide, iodide, sulfide, so on and so forth. Those monatomic ions, anions, ending in IDE, and replace it with the suffix "ic." We've got this hydro prefix in front of it. We don't call it hydrogen chloric acid, it's hydrochloric. So we're just going to add the prefix hydro. And again, this applies to all ions that end in "ide." Make a note about the Cn- ion. Most of our hydro something ic acids will be binary, meaning just 2 atoms present, but the Cn- ion is called cyanide. Most of our polyatomics end in "ate" or "ite." Cyanide is an exception. It ends in IDE. So the acid, HCnAQ, would be called hydrocyanic acid. Definitely, again, put that in your notes somewhere. All right, let's look at our acids that contain anions that are oxyanions. We'll call them our oxyacids. HClO3. So we already talked about this. ClO3 is the chlorate ion. And we know that naming acids is all about looking at the ending of the anion. This acid is named chloric acid. So if we kind of think about how we, transitioned away from hydrogen chlorate, the name of this molecule, into chloric acid, the name of this aqueous solution. Basically, we just took the anion's name, chlorate, and we replaced the ending ATE with "ic." You might be wondering what on earth is going on over here with this really weird picture. This is just kind of a mnemonic device to try to help you remember this change from "ate" to "ic." It's "I ate something icky at the cafeteria." I know, it is eye roll inducing, but it definitely helps. So "ates" turn into "ics." The last type of acid we're going to need to name are the ones that have oxyanions ending in "ite." So as we mentioned before, ClO2 with a charge of -1 is the chlorite ion. We call this acid chlorous acid. Again, if we kind of look at what changes were made to the name in order to get the name of the acid, it looks like we just have kind of a swap of the endings again. So the anion ends with ITE, "ite." We're going to replace it with OUS, us. And many, many years ago, a student helped me with a mnemonic device, and they came up with, "You'll be aight if you come with us." I know, if you thought I ate something icky at the cafeteria was bad, this is definitely worse. But again, I'm sure it will prove to be helpful. All right, let's try to put this into practice, and let's work on naming a couple of acids and bases. So we've got a bunch of practice problems that will give you a chance to really work on both naming and taking the name and turning it back into the formula. So let's look at a handful of them together. We'll take a look at the first 4. All right. So we know that we're going to be naming acids and bases. So the first part of taking your formula and turning it into a name is determining, is this an acid or a base? Acids tend to have hydrogens at the front of their formula. Sometimes I'll call them leading hydrogens. They're often the first element that's listed. Bases are going to have hydroxides present. So if we take a look at question 1, hopefully it's pretty obvious that there's a hydroxide ion present. This has to be a base. There are no special naming rules for bases. We name them exactly the same way we would name the ionic compound. So NaOH, we actually talked about this one in the video, or in the PowerPoint, is sodium hydroxide. Let's make things a little bit more complicated. Hopefully you're recognizing the question 2 is an acid. You've got hydrogens up at the front of the formula. Okay, so naming an acid is all about knowing the name of the anion. SO3, definitely a polyatomic ion. And you've got a bunch of polyatomics listed over here on the right. So let's see if we can find SO3. Oh, there it is. SO3 with a charge of 2- is the sulfite ion. Okay, we've got those mnemonic devices to help us remember. Sulfite, ites turn to us's. The name of this acid you might think is sulfus acid, which I would take at this point in time. It's actually called sulfurous acid. And you might be wondering, where did that R come from? And it just has to kind of do with experience at this point. I know that is a terrible answer, but you're going to see that your sulfur polyatomics and your hydrogen polyatomics are going to carry around a couple extra letters. You'll get used to it. I will not try to trick you with giving you sulfurous and sulfus acid and ask you to choose. Again, if you're correctly converting the ite to us, there's a high likelihood I'm going to take your answer. All right, question 3, H2S. All right, that is definitely an acid. Those lead hydrogens. We have a monatomic ion, so that would be sulfide. What would be the name of this acid? Yeah, we would call this hydrosulfuric acid. Ides turn into hydro-X. And again, we see that kind of weird thing with the R being taken along. Again, we'll practice, you'll get used to it. Hydrosulfuric acid. Last one, we've got H2SO4. Another polyatomic. If we go back to the table, we can see SO4 with the charge of 2- is sulfate. What should be the name of H2SO4 as an acid? Yeah, this is sulfuric acid. And that's just really the thought process you need to go through. Find your polyatomic, look at its name, check the ending in particular. Ates turn into ix, ites turn into us's. All right, we'll do a couple of, let's just do 2 of these going in the opposite direction. We have hydrofluoric acid. Okay, so it ends in an ic and it's got the prefix hydro. There's a pretty good chance you're looking at just a simple binary acid. Fluoric must come from fluoride. So hydrofluoric acid would have the formula HF. Let's make it a little bit more complicated. Let's call it oxalic acid. Okay, so I know it ends with ic, so this must have been an 8 ion to begin with. And it's got to be polyatomic because I don't have the prefix hydro. So let's see. If we look at oxalates, here we go. Oxalate is C2O4 with a charge of 2-. This is an acid, so I know there'll be hydrogens present. If the oxalate ion has a charge of -2, how many H+ ions are we going to need to balance out that charge? Yeah, hopefully you're thinking 2. Oxalic acid would have the formula H2C2O4. All right, definitely keep practicing with this concept. Just like naming from first semester topics, it's all about repetition. The more practice you get in, the more confident you'll get with this material, and it'll stop being something that you really have to think about, and it will just start to become second nature. Good job with this, chemists. Thanks for tuning in, and I hope you found this helpful.